Hey everybody, Mr. Bowman here. In this video we're looking at 3.14 probability distributions. Our focus is on the merit questions for the 2024 exam. Just a reminder, I've got all of the merit questions for you in one place from past exams, so check out the link in the description to this video if you're keen to see the rest of those questions. So let's get into question number 21. And question 21 was a bit weird. So in the previous part for achieved, you had to go ahead and calculate this distribution. And I've got the working there for you. The merit part of this question, backing up this, is give two reasons why the probability distribution selected in part I is appropriate. So in the previous question, you had to choose a binomial distribution because it was going to be binomial. And this was all about if someone's belly button was an innie or an outie. And the question also then had some more information. 96% of the people had their respondents, and then we were dealing with a class of 30. So those are kind of the key facts from the question. Just put up a text box to help us with that because it is quite a wordy question. And I suppose of focus is you only needed to give two reasons. I'm going to go through four just so you know what possibilities there were, but there were four to give it. So I guess the first thing to think about is I'm going to start off my list of all the assumptions, all the things needed for a binomial distribution. And the first thing was there needed to be a fixed number of trials. There needed to be a constant probability. There needs to be, what were the other ones? There needs to be two possible outcomes, right? Two possible outcomes. And then finally, the events must be independent of each other. A really important thing to note at this point in time is if you just write down what we've did here, while they're all correct and you've done really well to remember all four assumptions, is you haven't linked it to the context of the scenario, so you're not going to get any marks for this. They won't even mark it. It'll just be a straight no marks. So for each of these here, I need to add in a sentence that links it to the context of the scenario. So I guess fixed number of trials, we want to talk about the 30 people in each class. That's what it relates to. So there are a fixed number of trials because there are 30 people in the class. So that's linking it back to the context. Same thing as well, constant probability. And that relates to the 96% innie and obviously 4% outie. So those are fixed probabilities in this case, right? So there is a fixed probability of success because we know that there is a 96% chance of a random person having an innie belly button. I don't know why they talked about belly buttons in this one here. It was a bit of a weird context of having, so we'll use my Grammarly add-in to fix that, or no, maybe not, it's just glitching. Okay, so done that one there. Now, two possible outcomes. This one's probably the easiest of them all. Like, your belly button is either classified as innie or outie. So that's your two outcomes. There are two possible outcomes in relation to the students' belly buttons being an innie or outie. And then finally, there has to be this idea of independence. And there's a slight disclaimer, but generally within a class, no one's going to be related or anything like that typically. So that means one person's belly button is going to be independent of the other person's belly button. And the off chances like identical twins or some siblings in the same class, which it doesn't really tell us about here, that might not be the case for those two or however many siblings there are. But in this case, there will be. So I think it's fair to say independent. In a class of 30 students, they are unlikely to be related, which means their belly buttons are going to be independent. Okay, so we're now into question number 22. So I've got question number 22 there. And of note, I just want to pass on, I've added in some information from the formula sheet. So that's how to calculate the height of a triangular distribution. So let's get into basically the question here. So we've got using the parameters given. So in this question here, they've told you what the maximum is, so the minimum, maximum, and the mode is. Estimate the probability that someone has belly button fluff that weighs less than 1.5 micrograms. So I guess the first thing to note is it specifically told us it's a triangular distribution, so we don't need to state our distribution choice. but it's always good to sketch your diagram to make sure the marker can give you the full marks. So there's my triangular distribution. I've made it up roughly. Per my parameters down here, I know my maximum and minimum, so that was 0 and 7.4. So my A value is going to be 0. My B value, which is my maximum, is going to be 7.4. Don't forget, you've always got your mode coming down the top there. We've given that there. That was 1 milligram. So don't forget that was your C value, which is your mode. And then finally, the question specifically talks about 1.5. So 1.5, let's draw that there. That's actually my X value, isn't it? And that's going to be 1.5. I've been asked about less than 1.5, which I'm going to shade it in. So we've actually been asked to calculate this area here. And I want to note it's going to be a bit difficult because that portion of my diagram is a trapezium. That's going to be a bit more annoying to calculate. So my plan of action, what I'm actually going to do is I'm going to calculate the area of this triangle here, and I'm going to do 1 minus that probability to find the remaining area. So that's probably going to be a bit easier here. So I guess the first step when you're doing triangular distribution is you've always got to calculate the height. So we're trying to find the height at this particular point here, and that's where these formulas come in. And we can see our line is in between B and C. So we're going to have to use the in between B and C formula, which is the one just over there. So let's jot that down as the first step. So my height is equal to 2 bracket B minus X over B minus A, and then another one B minus C. So I've got that there, and I know all my letters. I know my A, B, C, and X. I know all of those there. So let's plug those all in. So so it's going to be 2 times, we're going to do B minus X, so B minus X, so that's 7.4 minus 1.5. There's my closed bracket. I've then got B minus A. That's going to be 7.4 minus 0. So 7.4 minus 0. And then I've got B minus C. So that's going to be 7.4 minus 1. So I've got all of that. I'm going to plug that straight into my calculator as it is. And I'm getting 2492. And that there had a 4 dp rounding. I want to note when I recently marked an exam of classes of this, a lot of students for some reason stopped here, and I just want to write that's definitely a bad call. That's the height of your triangle. It's not the probability at the stage here. So let's get into that. So the probability, so just a reminder, we're trying to find the probability that X is less than 1.5, and we talked about that's going to be the probability, that's going to be 1 minus the probability that X was greater than 1.5. And this area here is this portion, the unshaded portion of the triangle, and that's just a triangle, so it's 1/2 of base times height. So that means my working is going to be 1 minus 1/2 of base times height. We then have to figure out the base and the height of this triangle. We've already done the height, but now the base is going to be the issue. So the base there is between 7.4 and 1.8, and also 1.5. So minus them together, that's going to be 5.9, isn't it? So that there will be 1 minus 1/2 times by 5.9 times by the height, 0.2492. And I'm going to plug that straight into my calculator. When I did that, I got to 0.2650. So that means the probability of this portion here was about 26%. So we're now on to question number 23. And I just want to note, these are probably questions you don't want coming up in your exam because they take a lot of time to do, particularly if you're doing it manually. And there's a higher risk of doing math errors, so they're not the funnest ones. So I suppose let's get to the question. We've got our table here, and we've been told it's a random discrete. So we're going to be using our random discrete variables. Just down below the question, I've just copied and pasted my random discrete section of the formulas sheet. That way you can kind of see it as we're doing. Basically, we've been given that the probability of C is 0.5. However, we've been asked to find, that's not the probability, that's the standard deviation, isn't it? We've been asked to find the standard deviation of variable t. So we're going to need to find that. And I suppose on the formula sheet here, we've got the standard deviation highlighted there. So the standard deviation, we're going to have to apply this messy formula here. And we're not going to do it all in one go. We're going to do it in its chunks. But basically, we're going to need the expected value of x squared. And we're then going to need the mean, which is the expected value of x. And then we have to square that afterwards. So we'll get rid of those. So these are the first two things we need to calculate. once we've got that, it's pretty easy to figure out, but we're going to need to do that. So let's start off with the expected value of x squared, or t in our case. So to help me with this part of the question, what I'm going to do is I'm going to add in a t squared part of my column. So t squared, and I'm just going to square all of these numbers, and I'm going to rewrite them down below. So 0 squared stays as 0, 1 squared stays as 1, 2 squared becomes 4, 3 squared becomes 9, 4 squared is 16, 5 squared is 25, and 6 squared is 36. So I've got the t squared part of my formula. I now need to plug it in to kind of the rest of the formula, and that's where this part here comes in. So basically what we're going to be doing is we're going to go probability times t squared plus probability times t squared plus probability times t squared, and we're going to repeat that for our whole thing. And then we're going to add them up to see what that's going to come to. So we're going to write down E, but this time we're going to take away the x squared, put in t squared because that's the variable, and we're going to start doing that. So we're going to go multiply these two numbers here. That's just 0, so we can ignore it. Multiply these two numbers together. That's just going to be 0.271, and then we're going to add on these two numbers multiplied together. So 0.264 times 4. We're then going to add on the next lot, so that's 0.185 times 9. We then need to add on that one there, so it's going to be 0.095 times 16, and then the next lot there, we're going to plus 0.039 times 25, and then finally add on 0.017 times 36. So I plugged that all into my calculator. I'm just checking my answer. I got 6.099 when I did that. So I now need to do the same. So I've got that one there. I now need to find x squared. So instead of multiplying the top and the bottom, I now need to multiply these two up here. So I'm not dealing with the square number anymore. I'm just dealing with the regular number 0 through 6. So let's get into that now. So the expected value of x is going to be equal to, so 0 times that is still 0, so we can ignore that. 1 times 0.27 is 0.271, so 0.271, we're going to add on 2 times 0.264, I'm then going to add on 3 times 0.185 plus 4 times 0.095 plus 5 times 0.039, and then finally plus 6 times 0.017. So you can see these calculations are really similar. So that and that really similar to each other. You're just using the square number or the regular number, depending on which way around you're doing it. So again, got my expected value of x out, my mean basically, putting that into my calculator, 2.031. I now get back to my formula down here, so I can calculate the square root of t through this. So the square root, or the standard deviation of t, I just noticed that x there probably should be a t there. So the standard deviation of t is going to be equal to, and if you look at the formula, it's going to be the expected value of x squared, so that's this number up here, 6.099, and then it's minusing the which is this number here, squared. So minus 2.031 squared. If you're doing this on your calculator, there's a higher risk of doing a math error, so don't forget to whip those around in a bracket if you're doing it on your calculator. And when I did that, I got 1.405, and that there was rounded to 3 decimal points. So I've done all of the hard mahi. I've asked the question, so I've calculated the t. Now the question says show that C has a lower standard deviation, which we have, right? Because 0.5 is certainly a lot lower than 1.4 basically. And then it says give one reason why this might be the case. And that's where it's going to be a bit tricky. So I guess the first thing to note, we're going to have to explain the first part of the answer. So let's just state that C is lower. So we can see the standard deviation of C is less than the standard deviation of t, as 0.5 is less than 1.405. So that's the first thing. The next thing is to state the reason. And this is when the context of the question is going to be a bit different. So these ones here go from 0 to 6, right? Whereas in the question, the maximum number of nights in this other city is 3 days. So that means for C, your table would have been like 0, 1, 2, 3. That's all it would have been. It wouldn't have 4, 5, 6. So what we can see is just by comparing the data, we can see City T, I think it was, they had a much wider range of possibilities. It could have gone from 0 all the way to 6. So a much larger possible variation. Whereas City C, if we want to call that, could have gone from 0 to 3. So a smaller range of variation. So because of that, the possible variation that could occur, 0 to 6 versus 0 to 3, we can see there's just less variation that's going to happen in City C versus City T. So we're going to write that down. So we'll write C has possible values, oh gosh, I've run out of room there, possible values of 0, 1, 2, 3, which have a smaller range, than T of 1, oh sorry, it should be 0, right? 0, 1, 2, 3, 4, 5, and 6. And then we just want to link it back to the variation. Because of this, T would have more variation and a higher standard deviation. I'll stop there. Probably could have put it in a better sentence, but just running out of room there. Okay, so we're now on to question number 24. And this is one of the easier merit questions I've seen, so hopefully one like this comes up for you. But you've been told it's a percent distribution, you've been told about the mean. And then you've been asked to calculate and estimate that the probability of the general population was at least once in a day. So this one here is going to be a bit tricky to do. So I guess the first thing to note, if you're drawing down like a number line, which I do encourage you to do for binomial distribution and percent distribution questions, at least once a day means you're trying to find out this portion here. And the way the calculator and percent distributions work is you kind of start from here and you go up to the number. So that means if we were doing the calculation, we could only really figure out the probability that x was equal to 0. And that there x is equal to 1 or more, that's the probability you're trying to find out. So from that relationship, we know that the probability that x was, at least 1 would have been equal to 1 minus the probability that x is equal to 0. So that was kind of the trick to that question. It was a 1, I call it a 1 minus p trick in my class, because you're finding at least. The other trick of the question was, I suppose let's get into the question. For your percent distribution, we know that x is equal to 0 for my calculator, because I need that 0 to work. And I know my lambda from the question was 2.8. But I want to pause there to think, lambda has to be of the correct time interval, the correct interval, right? So my lambda here was a per week number. However, the question here asks us about a day. So we need to shift from a weekly number to a daily number. So to do that, I'm going to go divide by 7, which gets me to 0.4. And that's my true calculator input. So when I put that into my calculator, I figured out that the probability that x was equal to 0 was equal to 0.6703. So that was the probability of x being equal to 0. I can now go 1 minus p to find out the probability that x was greater than 1, or at least 1. So we've got probability that x was at least 1 is going to be equal to 1 minus that number. So there's a few tricks there, but if you can catch them, really crazy question. So 0.3397. And I should note both of those numbers were impacted by my 4dp rounding. Okay, so we're now on to question number 25, and it's a bit of a typey question, so I've got my text box up again. But basically, this question carries on from the mean belly button type stuff, the washes per week. So to apply the distribution, we have to make at least one assumption, identify one assumption that has been made, also one assumption that may be invalid, and discuss why this is the case. So I guess the first thing to note is there's a few issues with the use of a percent distribution here, but the big one is percent distributions have to be random. So we're assuming that these belly button washes are random of each other. So we're going to state that here. So the use of a percent distribution requires us to assume that washing belly buttons is random. So I spelt percent wrong. We'll see if it fixes it this time. It does. Perfect. Okay, and I think this isn't going to be the case. You know, if you think of earthquakes are random because they happen any time of the day, right? If you think of rain can be random because it happens any time of the day, really. But are belly button washes random? Are they going to happen at any time of the day? And this is where I think the use falls apart, because I think most people's kind of, you know, personal hygiene routines, either, you know, people shower in the evening or shower in the night. There's no randomness to that time. During your daily interval, the washing of a belly button is not random. It normally happens within your daily routine. So because of that, I think this randomness assumption falls down, because I don't think there is randomness to it. So let's start on that. So washing, including a person's belly button, may not be random, as it would form part of a person's daily washing routine. This means it might be predictable, i.e. in the morning or evening, depending on when a person normally washes. This might suggest that the use of a percent distribution may not be appropriate. So I think that was a nice sentence. So this here was a nice cruisy one. A lot of people might want to talk about independence here, but I think the randomness chat is a really, really good one. And it's the one that Model Arts has talked about as well. Okay, so we're now on to the final merit question for this video, question 26, and this one is always the hard one. Students tend to really struggle with these ones here. But we've got here a 2012 study collected from 138 people in 2011. It collected information about their belly button habits. This was defined the frequency during 7 days. So basically, in a week, how many times did someone wash their belly button? We got a whole bunch of people on 0, a whole bunch of people on 7. A whole bunch of people on 9, and I bet it's, you know, most of the people here, 0, it's because they don't consciously wash their belly button. 7, because they probably consciously do it every single day, and then a scattering of randomness. Basically, what they've done is they've thought, hey, this could be a percent distribution, so they've done a simulation, a theoretical model. So if they followed a probability simulation, the normal distribution, what would it look like? And that's what these grey lines are here. That's their different things. And you see in the question here, it says they've done the simulation 1,000 times. So it's hard to see it. It just looks like a big cloud, but this is actually, you know, in theory, this is 1,000 different grey lines, you know, all stacked on each other to show you the possible variation that might have occurred if you replicated this sample of 138 people. And basically, it's just the question. It really is simple. Explain what the grey band in figure 3b is showing. So these questions here, it's not just about the grey band, because remember, the grey band is your simulation. So if you want to get full marks for these questions, you need to discuss the simulation itself. So when I like to do these questions, we'll do a bit of a sentence starter for each of them. So I like to, firstly, I like to explain the simulation. So that's my first thing that I always like to do here, because they're also intertwined. Once I've explained the simulation, I always want to get in a comment about my sample size and my sampling variability, because that's what this is trying to show, right? That grey band shows you the possible variation that may have happened. And then finally, once I've done that, I then like to put in a comment about, you know, the actual grey band itself. So let's go purpose/function of the grey band. And I think if you discuss those three things, that's, you know, a pretty good answer, and you get 3 marks. And each of them doesn't have to be a full paragraph. It's maybe a sentence or 2 for each of them, and that will get you kind of the full merit mark of this case. If they give you a full page to write this, then, you know, that's an excellent question, and they'll have a higher expectation of you. But here, just because I saw the exam, you only had like half a page to write, so it wasn't going to be an E question. So I suppose the first thing to note is explain the simulation. So basically, there are 1,000 trials / 1,000 grey lines indicating or representing one simulation of another random 138 person study using a percent distribution model with a mean of 2.8 belly button washes per week. So that's kind of what the simulation is doing, right? It's the simulation with 138 person, so I've written a student, but that should be study, 138 person study, and we've done this 1,000 times using the certain parameters of a binomial distribution model. So we then want to maybe talk about what each grey line represents. We'll do that really specifically. So each simulation, or each grey line, represents one simulated 138 person study. Or simulated. There we go. Okay, so that's the first kind of thing. So I've discussed the context of the simulation. The next thing I want to talk about is, what it could show. So the 1,000 grey lines form a larger grey band, which shows us the possible variation in the distribution of washes per week of belly buttons. And specifically when using a percent distribution. So that's what it's trying to show us, right? And I guess the next part is we've got to talk about, well, what's the purpose of the grey band? So the grey band is going to show us, it will allow us to compare the actual data that we have, so this data up here, with what a percent distribution should have looked like, and then it will let us to figure out, is a percent distribution appropriate in this case? So that's why. So the grey band will allow us to compare the theoretical distribution with our actual distribution from, oh gosh, that's a bad spelling, from our sample of 138 people, and potentially assess the appropriateness of a percent distribution. If the grey band and actual distribution follow each other, then a percent distribution may be appropriate, or vice versa. That's the opposite. If they don't follow each other, they might not be there. There you go. So 3 short sentences, explain the simulation, talked about the sample variation, because that's kind of the point of it. It shows us the possible variation we'd expect to see, and that lets us make a decision. And then we've talked about, its purpose, its function is allow us to assess if the actual distribution matches or roughly matches the theoretical percent distribution. So that wraps up all the merit questions of this video. This video was quite long in the end, 29 minutes, which is quite a big one for that. And I think that reflects just the nature of the wordy questions that came up in this exam. So hopefully you find them useful. If you're looking for more merit questions like this, don't forget to check out the link in the description to this video. And it's got kind of all the other merit questions from like 2019 or something like that onwards. So a heap of extra work for you to help with.